All right, so we're still working on approximating the area under a curve. Like I said yesterday, we didn't finish tables, so I want to show you one, but I want to show you something else first. I need my mouse clicker. Okay, we have this little thing called calculus in motion, and we can, I think it's that one. Okay, I can show you kind of digitally what's going on here. All right, so this is basically a polynomial. We can adjust all the values of A, B, C, and D, okay? When we are solving, I didn't show you this yesterday, okay? When we're solving for the area under a curve, we write it with this. It's called an integral, okay? It's basically an antiderivative. So this means the antiderivative from -2 to 1, okay, so that's where the red is, of the function. So that means you're calculating the area under the curve, okay? That is a left-handed approximation with one rectangle, okay? We can change it. Let's see, how 6. Okay, there are 6 left-handed rectangles, right? So you kind of get a visualization of what's going on there. The key here to get a perfect answer is to make the rectangles smaller and smaller and smaller until they go to what number? Yeah, there are an infinite number of them. Then you'll get a perfect answer. So a true integral will give us a perfect answer. It's the limit as n approaches infinity. The number of rectangles goes to infinity, and you can see it gets closer and closer, right? Okay, thanks for that answer. Awesome. Let's do 6 again. And there's the right-handed rectangles. You can see the difference there. The smaller answer would be the right-handed rectangles, yeah? In green. Okay. That was yesterday, and I'm going to show you a table. Here's the midpoint. How's that calculated? It is the middle of the rectangle top. Okay. Most of the time, like I said, you're going to see this in a table where you're given those values. But it's a possibility that you would have to calculate them. Okay, and then the fourth one is trapezoids. All right. And all these are basic geometric shape areas. Okay. The back what?
Line is at the left side of the
yeah, so the left end point here, left, you see?
Yeah.
Okay, so you would take the width times the left height to get the area on each of these and then add it up, right? On the right rectangles, it's the right height times the width. And the middle, you have the middle height times the width. Okay, that's what this black line's denoting. And then the trapezoids actually take into account the height of each spot here. So you actually have to use both sides of each trapezoid because they're the bases. And I'll show you that today. Okay. Does that kind of give you a good idea of what you're looking at? It's a little bit prettier than when I draw it. I'll give you that. Okay. No. And okay, ow. Okay, take your pick. Left or right-handed endpoint? Left? Fine. Okay. I have no idea what this looks like yet. Personally, I'm a geometer, so I picture things, so I draw it. Okay, and it doesn't need to be much. I know that it goes up, so hey, yay, look at that. Right? That's all I do. Throw it on paper because it helps me see. So if we're going to do a right endpoint approximation. We start at the right side. Somebody said right. I'm pretty sure of it. Yeah, well, I don't like left-handed people, so we changed the plan. Okay, there you go. So we're doing a right-handed approximation. I'm pretty sure I heard right, but I might have heard left and been wrong. Okay. All right, so this gives you kind of a good picture, right, of the rectangles. What's the width here? 0, yeah, 1, 0, 1, 2, 3. They're 1 wide each, right? No. But it makes it easy. That's all I can say. Yes, no, they don't have to be the same. What are the height of each of these? Knowing we're doing the right side. Okay, so this is 26. And, okay, do we worry about this one? No. Okay, it's a right endpoint. Don't worry about the left. Okay. So now you just have an area approximate. Don't forget the squiggles. Okay. Do your math. This one's easy. What was I thinking? Okay. There you go. Yeah. One way you can make this, if they're all the same width, okay, it's actually a faster calculation. I wouldn't say it's easier. Just add the heights up. And then multiply on the outside by the width. That's an option. All right. Okay, so this was a right endpoint. There we go. Okay, good. Let me see if there's a midpoint example in here somewheres. Ooh, there is. Calculate L6, no, M6. So that'll be midpoint with 6 subintervals for x equals negative, or f of x equals x to the negative 1 on 2, 4. And I'm going to change that a little bit. Okay. No, stupid hand. M6, okay. Okay, midpoint with 6 subintervals, right? Should I make it easy on you? Yeah. Hold on a second. 4. Yeah, so this would be a midpoint. And this would be 6 rectangles or subintervals. Okay, remember that word, subintervals? You're going to have to use it, okay?
How do you know if they want to use like rectangles or?
Well, you either have a left endpoint, a right endpoint, or a midpoint. Those are all rectangles or trapezoidal. Okay. Okay, on the AP exam, they don't use this. They would say, well, they would actually write it out. Calculate the midpoint approximation of this on an interval. No, midpoint is the midpoint approximation. It would say trapezoid or left-handed or right-handed, yes. Like I said, I'll show you some of those. It shows up just about every year on the free response. This does. Easy points, right? Okay. What does that look like? This is... That's square root. This is the same as 1 over x, remember? All right, so we're going from 2 to 4. Yeah, this is not... Okay. So, okay, we need 6 subintervals out of 2 places. So each of them is 1/3, right? Yeah, 2 over 6. That's 6 rectangles. Yeah. Okay, the midpoints. This is where it's going to get a little bit messy mathematically. That's what your rectangles are going to look like. So we're not actually going to use 2 1/3. We have to use right in the middle of those two. Okay. I know. You'll get better at it. Okay. So that's what it looks like. How wide are our rectangles? I think we determined 1/3. So, right, 2 over 6. 2 wide, 6. Okay, so like I said before, you can just throw that out front since they're all the same. Right? All right, here's the fun part. We got to do some math. Okay, what's our first midpoint value? That's the question of the day. Okay, this is 2 1/3, correct? What's halfway? What's half of a third? The 1/6, yeah. So you're going to evaluate f at 2 1/6 to get that height, right? Probably easier if you change that to an improper fraction. And I'll show you why. 13 over 6? Are we okay with that?
I don't see how you got that though.
Okay. 2 1/3. You have to go right in the middle. Between 2 1/3 and 2, that's 2 1/6. Okay. So you can break these into 1/6, and that's going to give you your middles. Okay. What's the next middle? So we have 1/6, 2/6, 3/6 is a half, right? 2 1/2, so that's 5 over 2. 4 5/6 is 17 over 6. You can leave that in 1/6 if you want. I think it's going up 2/6 every time, right? Because if I wrote this in 1/6, it would be 15 over 6. So 13, 15, 17. Now we have 19. 21. 1, 2, 3, 4, 5. Big parentheses for emphasis. Do you understand where I got those numbers?
Yeah.
So you're breaking it into halvesies. Those are your midpoints, right? So you have 2 and a sixth. 2 and 2/6 is 2 1/3. So basically every other sixth is going to be your midpoint. Okay, what's f of 13 over 6? Okay, this one actually.
Well, wait, one don't you just flip it?
Yeah, you just flip it.
Oh, all right.
It is easier than you think. So we get 1/3 times 6/13 plus 6/15, 6/17. Anybody want to find us a common denominator for all these prime numbers? Yeah, I'm pretty sure you are. Not. Okay. Just use your calculator at that point. Okay. Well, that's a free response. What do you do with that answer? Bye-bye, we're done. Okay, so, yeah, no, this could totally be a non-calculator problem. You just leave your answer like that. Okay, don't touch it. No touchy. All right, so do you think you can handle a midpoint? It's just another left-right midpoint. Okay. Rectangles. Use rectangle area, length times width, right? Okay, let's do a trapezoid problem. Do you know how to calculate trapezoid area? Mm-hmm. You got it. And I think I'm going to have to make one up here, unless I go to 7.8. There we go. Let me think of a function. Okay. Calculate thanks. It's hand. It's just, yeah, I'm sure it is. It's probably not the hand issue. Okay, calculate. Remember, this means we're going to call this the integral from 1 to 4 of the square root of x. Okay, that is saying area under the curve. It's just the best way to write it. Okay, it's an antiderivative. So we could actually do this problem with our antiderivatives, unless I say using 3 trapezoids of equal, oh, that's not a Q. Okay, equal height. Okay, it could also say 3 subintervals. All right, so trapezoid area. Let's draw a picture here. H base 1 plus base 2 over 2. I guess it's going to be different. We have to tip it on edge. Okay, so when we actually do these problems, the trapezoid's going to be here. Yeah, base 2, base 1, H. Okay. No. These are more accurate, obviously, right? Because they're going to follow the curve more closely. So, again, I like to dream, so I draw the function. Unfortunately, I gave you 3 trapezoids. They're all of equal height. Yeah. Yay. Am I getting to you? Yeah. Yeah. Okay. So all right. So we can see those trapezoids are going to follow the curve better, right? Okay. The width of each one is 1, right? Okay, glad we could get past that. What's the height of each of those? Now this is where we have to use all 4 of them. Okay. That height is f of 1, correct? Which is the square root of 1, which is 1. Yeah? Sorry. I would make myself because you have to have both sides for a trapezoid, base 1 and base 2. Okay, this is f of 2, root 2, yeah? And this is 2. You got those? All right. We have 4 formulae to write, three formulas to write. Whoop. Every time you go out, you have to make that sound effect. Whoop. Whoop. Never mind. Mine was funny. Everybody's like, whoop. I think you should do it just for fun. Everybody would laugh.
Yeah, she'd be like, oh,
Nice try.
That would be hilarious. Okay, trapezoid A. Let's use colors. Okay, that one there, what's the height? 1, base 1 plus base 2 over 2. You will get very good at writing these out. Okay. Another color. And then the next one.
all of them are gonna just have the 1 in front, right?
Yeah.
Yeah, they're all the same height
Wait, why is it in
because they're formula. Well, the reasoning is you're averaging the height of the bases. You're making this a rectangle is what you're doing. Okay. Yeah, so you average these 2 numbers, and it makes, like right here, base times height. Okay, last one. Oh, let's use green. What you don't like? You can't, how can you not see that from?
Neon green.
Yeah, neon green. How about that? Nope. Throw one. You probably can't see that either.
Okay, I know what it is.
But you know what? I'm just going to use red. 1, 2, 3, 4, colors. It's just highlighted. Boom. Okay, good. Okay, now, no calculator, obviously we're not going to do this. Unless you know the decimal approximations. Anybody?
Nope.
1.414 and?
Nope.
1.718. Thank you. But otherwise, notice you can also write this. Okay, there's a 1 and a 2 in every one of them, right? Some people find it easier to do that. Because this is all we're going to get. Notice that you have 2 of each of the combined ones. Okay? So there's a little shortcut trick if you get good at these. if they're all the same height, put that all out front, and then just write the endpoints, and then 2 of every height. Okay. You can put this as 2 root 2s and 2 root 3s. And that would be 3, right? Okay, so lots of ways to write it. Shortcuts. Yeah, it's right all the way. Okay. So, yeah, you can leave it here. Some people actually write it like this initially. My Calc BC students got to the point where they were just writing this answer without looking at it. Okay, like I said, you'll get good at it. Okay. And again, keep in mind it could be given to you on a graph, it could be given to you on a table or a function. Okay. Let me give you one little more piece of info that you're going to see. This is a good one. All right. Let's see. If I give you a velocity function, let's call this 20, 10, 30, 40. We're in meters per second. And we're going to go 1 second, at 3, and at 6. This is seconds. Okay. So this is a velocity function. Of course it is. Okay. The question you might find yourself looking at is calculate distance traveled. Think of your relationships here. Not your boyfriends and girlfriends. No. This is no. Let's leave them outside. Okay, thank you. We need no drama here. Think position, velocity, acceleration. What do I do to velocity to get position? Which is the area under the curve, right? So this is the curve. Okay. It's not a curve, it's a bunch of lines, but it's the same idea. Okay. So this is a position. Okay. Is the antiderivative or integral of velocity. Okay. Translation? Area under curve. Okay, can we do geometry now? Yes, we can. With 3 rectangles, we need to calculate areas of, right? Now this one we can show with the equals because those are rectangles. So what's the size of this one? 15, 15, 15, Try to keep up here. Don't you see? No, I didn't think so. So what's this one? 1 by 20? Or no X's. Those are reserved now. We're not in 5th grade anymore. Okay, and 3 by 30. And survey says themselves.
Are you sure? 90 plus 80 plus 20. 190. Yep. Finally, it's not going to interpret those units in context with that. So, it's going to be right and a point. Finally, a point. Let's see, you're writing the workout, you're writing the answer to the next problem, okay? Are we good? Because I'm done. If you're not good, then we need to talk. Okay, you have a sheet I gave you? On the front is all the area problems. Do it. On the back? Yeah. There's an AP problem. Can I see that? There's two actually. One of them deals directly with what I just showed you. And if you look at letter C, here's a trapezoidal sum with 3 subintervals indicated by the table to approximate the position of the train at time 12. Okay, so you're going to use a trapezoidal sum there. I want you to cross out A. No, A is definitely a possibility. Well, A can be that's average rate of change from 2 to 8. Okay. B is no, what's that called? Intermediate value theorem, IVT. We're on the back here. So A is an average rate of change problem. B is an intermediate value theorem problem. C, we just did, area. And D is related rates. Oh, don't do that. So we're talking flags here if you write this down. A, B, C, D, any questions? Who is the trapezoidal sum? Okay. These are called, and that is probably something I should write down for you. In mathematical speak, they're called Riemann sums. Riemann was a very smart person. Oh, man alive. Didn't know who had that kind of stuff. That man was pretty intelligent. He was the first one to come up with this stuff. Riemann. Those Riemann sums. Okay, next full response strategy. A. Yeah, I'm just leaving you hanging here. Yeah, you got it. That's derivative. Okay, finding one of the maxes. What do you need? Derivative equals 0 and change in sign, one or the other, right? Okay, that's A. Find the minimum max. B is a mean value theorem problem. Let's see if you can figure that one out. And C is a derivative chain rule. Derivative chain rule. And pretty sure I need to cross out B because we haven't gone over U substitution. Okay, you got strategies? Tomorrow we're going to come and we're going to talk about this a little bit, and I'm going to give you some time to work on it. It's more knowledge I think that you have it smashed down, solid, clean, and good. Out. Okay, then. Thanks for the response. We'll wrap this